So I do want to let you know that we are now recording this portion of the webinar, and I'd like to introduce Dr. Michael Splash. He's a professional engineer and senior hydrologist with Dragon Corporation. Dragon Corporation has decades of experience in working in environmental consulting for a variety of industries, including agriculture and including dairy farms. And today, Dr. Splash is going to walk us through looking at nitrates in groundwater and how do you determine whose problem it is. And with that, I'm going to turn it over to Dr. Splash.
Thanks, Jamie. I'm actually doing this webinar from a location where we just had to put a water treatment system on my daughter's cottage. So I feel for the issue, and I've been on both sides. We've done a lot of work in groundwater related to dairies. I just want to make sure that you understand that this is showing the way that we generally approach a question of groundwater impact, and it's been successful. We're not going to go into a great amount of detail, but if you have questions, I can answer it. This is going to be kind of a hydrogeology 101 for those people who are interested in understanding how groundwater moves and how chemicals move in the groundwater. So the key here is that I want to use my experience in court, that I've been involved in several contamination lawsuits, starting back before Dragon Corporation was Dragon Corporation in the late 1980s. And basically, they're all the same in terms of it's groundwater, there's a chemical involved, where did it come from, where is it going, and so on. So I started off actually doing research in groundwater surface water interaction back in the 1970s, and part of my PhD thesis related to nitrate and phosphate impacts in southwestern Ontario. And I kind of got deeper into groundwater with time, and since 1992 I've been working with Dragon full-time on groundwater issues, and we've done a lot of court work on permitting for large dairies, for sugar beet operations, and the regular things that the EPA are interested, like landfills, industrial releases, gasoline releases, and so on. And I've appeared in a lot of different courts, so I've gotten to know what works and what doesn't work in an investigation in terms of having a convincing argument. So I started working in the hydrologic cycle and trying to figure out how water moved from the atmosphere into the ground, and my early work was related to where did the water in surface water or streams come from. And back in the 1970s, this was kind of the equipment I used looking at agricultural impact, and I wasn't very good at building structures in the streams, and that one washed away on the first storm, but I got better at it with time, and we use things like naturally occurring isotopes in the water molecule to figure out how the groundwater got to the stream and what proportion was in the stream. By 1984, we had gotten a little more sophisticated in our work, but back in the early 70s, the late 70s, this work was recognized, and this is in French, but you can see a revolution that people didn't really understand that most of the water that went to surface water bodies was groundwater, even during storms and snowmelt runoff. So it's taken a while for that to get into the mainstream, and we can see some of the recent U.S. Geological Survey reports on the Mississippi River, for example, in Chesapeake Bay, where they're finally recognizing that the nitrates aren't going down in the surface water bodies, because it's a groundwater issue to a large extent. So that's kind of my background in coming to talking about nitrates in groundwater and how you evaluate them. And you know, we're drawn to this by looking at the Yakima Valley investigations and whether they were using good science and clear objectives. And you'll see that a lot of the objectives that the EPA used are the types of things that we want to go about doing, but the question is it done correctly? So for the Yakima site, the objectives that the EPA had in their investigation in 2013, where they actually put in some observation wells and did some groundwater flow directions and so on. They wanted to figure out which way is groundwater flowing, and we'll see why that's important. What's up gradient, what's down gradient, that's important. And whether there's perched aquifer, that means some saturated zone above the main saturated zone. And then in the fact sheet that I showed you before, they wanted to identify potential sources and use scientific techniques to track where the nitrate came from and to do some tracing. So with that in mind, I want to go about how we typically do an investigation and some key things to look at when you see investigations that are done. So for a nitrate study, you need to know 4 things. Is there a source? Is there a completed pathway? Does the timing make sense from the source to the completed pathway? And does the glove fit? Are there anything else that doesn't make sense in the argument? So the first thing we do is investigate soil and groundwater. We advance soil borings, we install monitoring wells, we determine groundwater flow, and we test water quality. And I'll show you a little bit on each one of these. So we advance soil borings using standard methods, and this is kind of a thing that you need to keep in mind, that always you're trying to make sure that your data is not a point of contention. How you got the data is very important. So we always use methods that do not compromise the sample integrity, whether it's a soil or a groundwater sample, and it's a method that's acceptable to the regulatory agency that you're dealing with. You don't want to be sidetracked on you didn't get that sample in an appropriate manner. So once you do borings, you install monitoring wells that allow you to obtain groundwater samples and to determine the direction of groundwater flow. And again, we use methods that meet the regulator requirements to sample these wells. And it's pretty standard. You're not giving in to anything by using these standard methods. When we're determining groundwater flow, we have to measure water levels in wells, and we figure out basically what's the surface of the top of the saturated zone. Where are the water levels that we find, and what surface does that represent? But one of the things that goes wrong often is that the wells are not at the appropriate levels. You might have wells that are too deep, wells that are too shallow, not enough wells in a vertical sense to interpret whether it's a complex or a simple groundwater flow system. So even though this is not rocket science, it's often an error that we see in investigations. And then once we have water levels, and this little map indicates wells where we have water levels, you draw what we call contours. They're lines that represent the elevation of the, say, the water table. And it's kind of like contours that topographic contours on a topographic map for a hill. Groundwater tends to flow from the high water levels to the low water levels. And there's some rules for drawing what we call a flow net, which is the contours and arrows indicating flow. And Generally, the flow lines are at 90 degrees to the contour lines, and they indicate flow from the higher levels to the lower levels, lower areas. So the up gradient zones are the highest levels, the down gradient zones are the lowest levels. And those lines never cross. They I just got a lot of feedback there. The flow lines don't cross, so they generally will tell you whether a source can cause an impact. And on that map we had on the previous page, if there's a source at A, can it cause an impact at B? And the answer is no, because the groundwater doesn't flow from A to B. It flows along those flow lines. So that's something that we always look at in evaluating a site. What's up gradient, what's down gradient, where are the flow lines coming from and going to? We evaluate soil and groundwater quality using methods that meet the regulator requirements. So we use standard methods so that the data are beyond question in terms of how you got the data. And then once you have some information, if you have got an impact in the soil or impact in the groundwater, look at the combination in relationship to whether you're up gradient or down gradient. So if it's in the soil and it's in the groundwater on a particular property, including the up gradient property boundary, it means that potentially this is a source, but there's also a source up gradient. If you've got it in the soil and in the groundwater, but not on the up gradient property, then the source is on this particular property, and so on. So you can use kind of logic to figure out, you know, is this a source? Is it the only source? If it is the source, then we say we need to put our arms around the problem. And what this means is we ring the suspect source with borings and wells. We investigate as deep as required, and we step out as far as required in order to determine the extent of the impact. So what I've tried to indicate here is that you've got a suspect source, and I'm colorblind, so if I make mistakes on this, please accept my apology, but I think I've got it right. The orange rectangle is a suspect source, and we're looking from above. We want to determine if there's impact out away from it. The initial borings we do are in red. X's indicate that they don't meet the regulatory standards, so you move out further. The white borings are the next set, and you keep going until they meet the regulatory standards, and that is delineating the impacted zone aerially. And you do the same thing vertically. You have to sample outward and downward until you don't have impact. And one of the things where we see problems is that the vertical extent of impact is not always totally delineated. So you need to make sure that you delineate to clean, and then you would have an area that would be impacted, and you know the extent of the problem. This is just a real quick look at an agricultural chemical site that we looked in Kansas that was impacted from nitrate from fertilizer. Just, you know, you go in, you need to understand the geology and the groundwater situation. In this case, we've gone down 16 feet to sand, going through some finer materials. And this is showing the concentration with depth and breadth of the nitrate. And in this particular case, people who did this investigation didn't go down deep enough because there were still exceedances. So you haven't put your arms around it. If you can put your arms around it, then you can step forward and figure out what you need to do. One of the questions that we're always asked and faced with is how much investigation is done. How many boreholes, how many wells, how many samples? Sometimes this is specified by the regulator. For example, if you're trying to dig a pit and you want to make sure that you've cleaned out all the impacted soil, the regulator may tell you how many samples to take on a wall of the pit, on the floor of the pit, and so on. If it's not specified, you need to be able to demonstrate that you know enough, that you've done enough. And what I always say, if I can predict what happens at the next bore, I've done enough, or the next well, then I've done enough. But you'll often get regulators and other groups that might oppose your operation to say, but what if I drill here? You know, like you've got borings every 500 feet. If I go in between them, I may find something. Or if you've got them every 100 feet, you know, they'll always ask you to close up the spacing. Is there a completed pathway? Can you get the chemicals from, or do the chemicals move from the identified source to a specified receptor, like a stream? So you look at the groundwater flow. You know, does source A cause impact at C? Potentially. There's groundwater flow in that direction. But sometimes if we look at a slice of the earth cross-section, the impacted zone doesn't extend all the way from A to C, even though the flow is in that direction. So you have to look at all the factors. Does the timing make sense? How fast does groundwater move, and how fast do chemicals move? Well, in the case of nitrates, nitrates move at the rate that groundwater moves. Some chemicals do not. Many chemicals do not move at the same rate. They move slower than the groundwater. So how fast does the groundwater move? We use an equation called Darcy's Law. Darcy's Law figures out the velocity of the groundwater, the average velocity, and it's made up of three factors: hydraulic conductivity, which is like permeability. How easily does water move through a geologic material? Hydraulic gradient, that's the how close on that groundwater flow map I showed you before are the contours. It's kind of like the slope of a hill. The steeper the hill, the faster it will move. And porosity is the amount of pore space. Generally, when we're speaking of sand, sandy or gravelly soil, that would have 30% porosity. If you're speaking of a rock, it could be a lot less. So groundwater moves slowly. It might move meters or tens of feet per year or hundreds of feet per year, but generally it is quite slow. On the left, we see sand, which is geologic material that moves fairly quickly. On the right, we see fractured rock that would also transport groundwater fairly quickly. But we can also have materials where it doesn't. And this is a case in a lot of the work that we've done in the lower Great Lakes area in dairy development, looking at whether manure ponds will have a potential for leaking. On the far left, we see a clayey soil that is fairly impermeable. The water would be moving through this soil at an imperceptible rate, so slow. And the middle one is a problem we often run into called fractured clays, where it looks like it's going to be a good location, but there are cracks in the soil that allow water to move fairly rapidly. And you can see the wet spots on the bottom of this pit. And then on the far right is it's a clay soil called the barbed clay, and it's got natural partings that are more permeable. So each site is different. You have to understand what the hydraulic conductivity is, and you have to use standard methods that are appropriate for the soil. For sandy soils, you use a different technique in the lab than you do for a clayey soil. In the field, there are lots of different methods to evaluate hydraulic conductivity, but it's got to be appropriate for the material in the site. And then we could do something like sensitivity analysis. Here you can see Darcy's Law up here, and we're trying to figure out just at a site what could the travel time and velocity be. And we know the source and the receptor are about 1,950 feet apart, and we look at various inputs for hydraulic gradient, porosity, and we figure out groundwater velocity, and we figure out travel times. Some travel times don't make any sense, so it means that one of your input values isn't appropriate. And this would be something we would do before we have any field data, just based on our experience to see what could be happening. And we can use this graphed out and get an idea of arrival times from a source to a receptor. Another approach is using some sort of dating method, and kind of the one that I grew up with was tritium dating, which is still appropriate. Tritium is a type of hydrogen atom that is radioactive. So in each water molecule, in each H2O, there can be, some of the hydrogens can be actually tritium, and the natural tritium concentrations are very low. This is the range of how we measure tritium in tritium units, where one tritium unit is one tritium atom in 10 to the power of 18, 10 with 18 zeros, hydrogen atoms. So it's very precise measurement that you need in a very specialized lab, but tritium decays naturally with a half-life of 12.3 years. So if you start off with a pound of tritium in 1960, in 1972 you'll have half a pound. In 1984 you'll have a quarter pound, and so on. So natural tritium levels back in the 50s were low. They were 25 or less. During the Cold War, due to atmospheric testing of nuclear weapons, the tritium concentration in precipitation in parts of North America went up to 3,000 tritium units. And because we know the decay rate, we can see water that was recharged in 1963, that if it started at 3,000, by now it will be something like 120 tritium units. And something that started in 1969 would be like maybe 15. In 1953, there'd be none left. So tritium allows us to figure out when the water entered, and it allows us to give another measurement of how quickly groundwater and therefore nitrate would be moving. I read in the Yakima site that they used sulfur hexafluoride, which is another anthropogenic or man-made chemical that can be used for dating. I didn't see how they compared that to other dating methods, though. So you can use other tracers to evaluate time or source. I've used hydrogen isotopes, other parts of the water molecule, oxygen isotopes in the water molecule. You can use nitrogen isotopes, chlorofluorocarbons, kind of stuff we used to use in our air conditioners, pharmaceuticals, caffeine, and other things to get an idea how quickly groundwater will move. Does the glove fit? Are there other possible sources of nitrate? And we know that there are. And do the concentrations make sense? When we look at a receptor, does it make sense that it came from, one specific source? Some of the legacy nitrates could be fertilizers, inorganic fertilizers. They could be sewage lagoons, landfills, and in the case of where I am right here, it's agricultural. So there are some legacy nitrates that you need to be able to look at and rule out or rule in as source of the impact at a receptor. The thing that helps us when we're in court proving a case is what we call a multidisciplinary approach. And we just finished a case that related to gasoline contamination, but the attorney at the end of the trial asked me, after taking my testimony for 2.5 days, how can you be so sure about everything? And the reason I'm sure about everything is that we look at it in many different ways. We talked about, in this case, some isotopes and some groundwater hydraulics. there are other things that you can do, other approaches, and the idea is there's only one truth out there, and you can try to get as close to it as you can by using different independent approaches. And that's what we tend to do on our investigations. So in investigating nitrates in groundwater, whose problem is it? My recommendations are always use standard methods so you can't be sidetracked on that issue. They have to be done correctly, and then you have to use good interpretation of the data. You know, is there a source? Rule it in or rule it out. Is there a completed pathway? Rule it in or rule it out. Does the timing make sense? Rule it in, rule it out. Does the glove fit? And all of this helps you to be more certain of the conclusions that you make. So that's my presentation, and I will entertain questions through Jamie if that's the way you want me to do it, or however you want me to proceed.
Great. Well, thank you, Dr. Splash. I think that was a very nice overview of how you look at determining where nitrates in groundwater have been coming from. Please remember, if you do have a question, to first take yourself off mute so that we can hear you. And then also please identify yourself as well. And while you're thinking of questions,